Happy day, everyone, and today we are talking about the bomb calorimeter. So this is actually an example. We will come right back to this. Let's do a little bit of notes, and then we can shift back to get an idea of how the bomb calorimeter actually works. So what is calorimetry? Well, all it is it's the process of measuring your heat transfer, and you use a calorimeter to do it. That's it. So it's measuring the heat transfer using a calorimeter from a reaction using a calorimeter. It consists of an insulated container, a thermometer, and a stirring rod. How is it used to calculate the energy change? So all we need to do is measure the temperature change. So once we know our delta T for a certain mass, so we need to make sure that we understand what the mass is of the reactant. So we use stoichiometry to determine the energy absorbed or released, and typically what the units are is in kilojoules. We can also use kilojoules per mole. We can use calories or kilocalories. Now, what's the difference between a simple calorimeter and a bomb calorimeter? Well, this coffee cup calorimeter, or simple calorimeter, demonstrates calorimetry at constant pressure. Now, I have a really easy way of remembering this because the word cup, so if you're just using one of those really, cheap styrofoam cups, it's CP, constant pressure. Okay, now, what you can change is you can actually adjust the volume or the mass, versus a bomb calorimeter is going to be a constant volume or a constant mass. So I'm going to explain that in just a little bit here. Calorimetry experiments can be performed at constant volume using what is called a bomb calorimeter. And it's not really a bomb as what you would think of a bomb. It's really just a chamber that they call the bomb. For example, a camera flash flashes the reaction of a zirconium magnesium wire with the oxygen that's in the bulb is an exothermic reaction. It releases heat and the bulb becomes hot. The reaction is taking place in a set volume in the bulb. Therefore, because it's a set volume, we say no work is done since our volume is constant. So we need an instrument of constant volume to be able to measure the total amount of energy change. So we use a bomb calorimeter. Okay, so we're going to take a look at the parts of the bomb calorimeter right down here. This kind of explains a little bit, but I want to make sure that you understand sometimes a problem will say that it's a bomb calorimeter, but there's nothing in the problem that would lead you to solve the problem any differently from a simple calorimeter. So just kind of keeping that in mind. So I'll explain that in just a little bit here. Okay. So number one, this is simply our source of current. So we need some type of direct current. Okay, let's take a look at what number two is. Well, number two just looks like it's something that's doing some stirring, so that is our stirrer. Number three, that looks like a thermometer. Okay, and then let's go down to number four. And number four is the solution that's inside of here. Well, it's a substance. It's actually just water. So this is interesting because typically in a simple calorimeter, we like to use water or aqueous solutions. And it's the same thing here. It's just water that's surrounding it. Okay, number five, so this is our bomb. Okay, that's like the bomb chamber that's there. So this is our quote-unquote bomb, or we can call it the reaction chamber. We can call it the reaction chamber. Okay, number six, so this is our ignition. So we know that we need some type of like resistance wire for igniting this. So that's our resistance wire for ignition. Okay, so that way, if we're trying to burn something, we would set it off up here, have a switch go off, and then we can get that burning on the inside of that bomb. And then remember what ends up happening is it'll release the heat to the outside, and then we can just record the water. So we're still just recording what's happening to the water in this situation. And all number seven is it is simply our insulation. That's it. Okay, now, you can see here that the equation is delta H equals cat instead of delta H equals MCAT. Well, what happened to the mass? Well, what happened to the mass is they actually put the mass in with the constant. And the C is actually the heat capacity. So the mass is incorporated in right with this heat capacity. It has the mass already in there. Okay, so that mass has been incorporated. So if they give you the heat capacity of the bomb they have figured it out already, and they give you the heat capacity of the bomb, that's when you're going to use the CAT equation, okay? And you'll know, and the reason why you'll know is because the units are going to be different. You're going to see, instead of using the gram amount, the gram unit will be gone, okay? So let's take a look and just do a couple of problems here. So this first one says that, well, first I want to make sure that I mention that what our bomb calorimeters used for. They are very much especially used for combustion reactions. Okay, and we know that combustion reactions are when things are burning. So I want you to remember that. And these tend to be negative delta H values because they are exothermic. Okay, so if you have an exothermic reaction where you're burning something, you're probably going to want to use a bomb calorimeter instead of a simple calorimeter. Okay. So it says since combustion reactions are usually exothermic, we know that the delta H is going to be a negative sign for these. Okay, so let's try two questions. And the first one, it says that we have a 0.5269 gram sample of octane, of C8H18, which is in gasoline. It's put in a bomb calorimeter. It has a heat capacity of 11.3 kilojoules per degree Celsius. There it is. There it is. Look at the units for this. Typically, when we talk about heat capacity, we would do joules or kilojoules per gram degree Celsius. Grams are missing, okay? And again, so grams, question mark, question mark? Well, it's missing because they've already incorporated it into that constant, okay? So this means that 11.3, so let's kind of break down what does this 11.3 mean. That means that 11.3 kilojoules of energy is required to do what? Well, to actually raise the temperature of everything in that calorimeter, including the water, to raise the temperature of the water, because there's water in this calorimeter, and all the other parts of the calorimeter, by how much? Well, it's that many kilojoules for every 1 degree Celsius. That's what that means, okay? So that's what that number is. The octane's ignited in the presence of oxygen. The temperature increase in the calorimeter is 2.25 degrees Celsius. How much energy is released per mole? Now be careful because it says energy per mole. So what I'm looking for is I'm actually looking for kilojoules per mole of C8H18, not just kilojoules, okay? So I'm actually looking for the kilojoules per mole. Now, I want you to keep this in mind, okay? Keep this in mind. So whenever you need kilojoules per mole, it's like needing grams per mole if you're trying to find molecular weight, or moles per liter if you didn't know that. So what you do is kilojoules, moles, kilojoules over moles. Okay, so what we're going to do is we're going to find the kilojoules, we're going to find the moles, and then we're going to divide our two numbers, all right? Well, in this situation here, so I know that it's telling me that it's a 0.5269 gram sample of the octane, but that's going to only give me the moles of octane. Okay, so that's what that can be used for. So I'm going to come back to that in just a second. But let's see if we can figure out what the kilojoules are. I don't know kilojoules, but I know kilojoules per degree Celsius. So I know it's 11.3 kilojoules per degree Celsius. So in order to just get kilojoules, guess what we need to do? All we need to do is multiply by the degree Celsius. So it's a simple, bridge type of problem. So I know it's 2.25 degrees Celsius. So if I multiply my 11.3 by the 2.25, I get 25.4 with 3 sig figs. And so that's my kilojoules. Not done yet, because remember, now I have kilojoules, moles, kilojoules over moles. Now I need the moles. Okay, so I'm going to take that 0.5269 gram. And by the way, you could do this all as a bridge if you really wanted to. And it's C8H18. Okay, and then don't forget, we're going to use 12.01 for the carbon, and we are going to use 1.008 for each hydrogen. 114.22 as my molar mass, grams per mole of the C8H18. So if I do the 0.5269 divided by my answer, I'm getting 0.0046, let's do 4 sig figs. So 0.004613, and that's the number of moles of my C8H18. Well, now I know kilojoules, now I know moles. All I need to do is divide. So 0.00 or 4.613 times 10 to the negative 3. 4613 moles So I'm going to do 25.4 divided by that answer. And this is giving me 5506 with 3 sig figs. So 5506 with 3 sig figs, it would be 5510. And my answer is in kilojoules. It is negative because that is energy that is going to be released. And so we don't want to forget here too, it's kilojoules per mole of the octane. Okay. All right, and last problem here is what I was explaining to you earlier. So it says compound B is burned in a bomb calorimeter that contains 1.50 liters of water, and there's 50 grams of compound B is burned, and then the temperature increases by 35 degrees Celsius. If the heat of combustion is 2150 kilojoules per mole, what's the molar mass of B? Oh, molar mass. Grams, moles, grams over moles. So remember, if you don't know, you're going to have to do grams over moles, and specifically grams of B and moles of B. Well, do I know either one of these? Yes, because they're telling us that they're burning 50 grams of B. So we automatically know that it's 50.0 grams of this substance B. Now I need to figure out the moles. Okay, now this 2150 kilojoules per mole, this can be very helpful. Okay, but I'm also seeing that they're giving me the liters of water, which could be the mass of water in my calorimeter. They're also giving me delta T. Something that they're not giving me, but I know, is my specific heat, or my heat capacity of water. So all I need to do in order to figure out delta H equals MCAT, so let's just go ahead and fill that in. So delta H is equal to MC delta T, and I'm going to show you that you could use a bridge for this as well. Some of you may find the bridge to be a little bit easier than this. Now remember, it's a milliliter is a gram of water. So if I take my decimal and move it 1, 2, 3 loops to the right, that gives me 1500 milliliters. Put that bar over that first zero to make it significant, or 1.50 times 10 to the third, same thing, okay? And so that's my mass of water, which is the same thing as grams, right? Okay, so I'm going to say 1500 grams of water. Now, if that's water, everything has to be water in this case. So my specific heat, kilojoules or joules? Well, because this is in kilojoules, let's use kilojoules. So 0.004184 kilojoules per gram degrees Celsius. And my temperature change, they said it increased by 35 degrees Celsius. Okay, so let's multiply this. And when we do, my grams cancel out, my Celsius cancels out, and I'm left with kilojoules. So I've got 1500 times the 0.004184 times the 35. And that gives me 3 sig figs. Actually, the temperature, sometimes people will use it and sometimes not. It's 35.0 anyway, so 3 sig figs on this. So 219.66, which would be 220 with a decimal point, and then that's in kilojoules. Okay, now, I'm still not there because I just figured out kilojoules, but that's not what I want. I want moles. Okay, there's something we didn't use. We did not use this value right here. And so all I need to do now is, if I know my kilojoules and I know my kilojoules per mole, that can tell me how many moles I actually must have reacted. So it's 2150 kilojoules for every mole. So this 220 divided by the 2150, and I get 0.102 moles. Okay, perfect. Because now I have my grams and I have my moles. I'm going to divide grams over moles. So 0.102 moles, and 50 divided by my answer gives me 489 grams per mole is substance B. Okay, now I'm going to show you the beauty of what is the bridge. Okay, I love the bridge. Now, this would be if we started with the grams. And so if we had started right here by saying, okay, I know my 50 grams of B, but I'm still looking for the moles, let's say. Okay, so I'm kind of going back and forget all of this. Well, here's what you could do instead. Okay, so I cannot start, I can't convert this 50 grams of compound B anyway, because I don't know where to go from there. There's nowhere I can go. But we already knew that we could switch this 1.5 liters and make that 1,500 grams. So watch if I started with this 1,500 grams instead, okay? So if I start with that, and this is grams of water, by the way, okay? So you do have to make sure that you get your substances right if you're going to do it this way. So what do I know that has grams? What number do I know that has grams of water in it? Well, ding, 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 4.184 or 0.004184 kilojoules per gram degree Celsius. So my because that's of water, okay, that's of water, so my grams of water cancels out. Now, the only thing is, I know that I actually want kilojoules, I want moles. This is what I'm trying to get, okay? So I want to get rid of kilojoules, and I also want to get rid of the degrees Celsius. So what I can do now is I look at my problem and I say, oh, wait a minute, it told me that it was 2150 kilojoules, so I can use that number, 2150 kilojoules for every mole. Brilliant, but I want to get rid of my degrees Celsius. So all I'm going to do is multiply by my 35.0 degrees Celsius, and now if I look at all of my units, everything canceled out except for moles. So let's check to see what we get. 1500 times the 0.004184 times the 35 degrees Celsius divided by the 2150. Oh, surprise! It gives me 0.102 moles, which is exactly what I said there, okay? So just to kind of give you an idea of how you can solve problems in two different ways and still be able to get the same answer. And the last thing I want to do is give you an idea of how a real bomb calorimeter would work. This is in a lab, so sounds like either a professor or a lab TA explaining how to use the bomb calorimeter to her students that are about to analyze something. So let's just take a listen here on this.
This is a bomb calorimeter. This is the actual piece of equipment that researchers use to calculate the energy content of either biodiesel or maybe even the potato chips that you had for lunch today. When they calculate the amount of energy, they're going to calculate it in heat units, which would either be joules or calories. I want you to look inside the bomb calorimeter. Inside here, you can see that there's a silver bucket. Water goes all in here. And this is actually the bomb. It's a smaller silver cylinder. What you do is put your fuel sample in there. Then, these two electrodes are connected to the bomb. These provide the spark that will ignite your sample. When your sample burns or combusts, that gives off energy. So how is the energy collected? Or how does a scientist figure out how much energy is being given off? Well, it's a closed system. There's a lid here that goes on top of this calorimeter. And what's in here, in the lid, is a stirrer. The stirrer is going to stir the water that's in this big pool here.
So remember what we were saying, it's still going to be the reaction heats the water that's surrounding it. So we're still using that same idea as we would in a regular a simple calorimeter as well.
That the heat given off from the sample is going to warm the water in a uniform way. This is the temperature probe. This goes down in the water also and measures the change in temperature, because as the sample is burned, it'll give off heat and the temperature of the water will increase. So the lid goes on, the sample is prepared. The last thing that you need to make a combustion reaction happen is oxygen. And at some point during the process, some oxygen is added by a tank that's connected to the calorimeter here. So we are going to burn a sample of the biodiesel that you've prepared and get some feedback on the energy content of it. You'll be able to use this to compare it to petroleum-based fuels like octane.
Okay, and so that's basically how the bomb calorimeter works. Hope this lesson was helpful to you. Happy day, everyone.